Welcome to the Apron Academy. This video is specially designed for the dietitian in training, also known as the RD-to-be. Today we're talking about biotin. More scary structures, but it's going to be good. All right, first I just want to talk about where we can find biotin. We can find it in cooked egg yolks, nuts, legumes. Interestingly, mammals cannot synthesize it, so we're not going to find it in a whole lot of meats. One fun fact that I want to mention is how they found out about biotin was people were eating raw egg whites, and the avidin in these raw egg whites was bound to biotin, and it depleted the absorption of biotin, so saw a deficiency in this. So now back to these chemical structures. This here is our biotin, and I'm going to explain what this is in just a second, but it's first very important to know this next phrase that I'm about to say. Biotin is covalently attached to its protein partners. This is so important. No other vitamin does this. Now, biotin is bound at the lysine amino acid in protein, so bound right here. This is where this attaches. You eat the whole protein, and then the biotin is attached there at the lysine. With peptidases, they break down our protein in what we end up with is biotin. Once biotin is broken down, and I say broken down, but it's more broken away from the lysine, this occurs because of biotinidase. That is what breaks it apart. And we'll talk about the biotinidase in just a moment. So biotin cleaves off the lysine by the biotinase, and then we have free biotin. So what does the free biotin do? It is absorbed into our body through the SMVT transporter or through passive diffusion. Now, it has two functions. The first is it acts as a cofactor for 5 carboxylases, and I'll talk about what those 5 carboxylases are in just a sec. But it works to synthesize fatty acids, gluconeogenesis, etc. So very important. And then our second function is that biotin binds to histones, and therefore this alters our gene expression. So first, we have this. This is our biotin acting as a cofactor. So I need to mention here that, we have to add on the biotin to the carboxylases. How do we do that? This is one of our carboxylases. You remember the biotin above. This is our biotin. So it gets attached, but how does it do that? Hollow carboxylase synthetase. That is how the biotin attaches to this carboxylase. Hollow carboxylase synthetase is what covalently attaches biotin to the enzyme partners. All right, so I never really do this. I normally keep very chemically structured, very much so this is what it is, but I did want to just do something a little fun this time. So here's some people. So we have our carboxylases. This is any one of the 5. And they are assigned an important project at work. This has to be a group project, but they are the first assigned to it. And because they're the only one assigned to it, they can't really do anything. They can't really put in any work. So the holocarboxylase synthase is our kind of facilitator, and he says to the carboxylases, hey, you need to team up with biotin. So the holocarboxylase synthase sends biotin over to the carboxylases, and of course you can see that they're covalently attached. So when the work project is done, they get to this point, they've done all the work that they need to, and then we have this biotinidase. I mentioned that at the beginning. This is what breaks them apart or breaks it away. So the biotinidase tells the biotin, all right, you can leave now, thanks. So, I don't know, I just thought about this as I was working on biotin, and I thought it was a fun way to remember. Just important to remember that biotinidase will cleave off the biotin from its enzyme partner, and that, I guess overall remembering, holocarboxylase synthase adds biotin on, and biotinidase takes the biotin off. Now, this is nothing to be afraid of because I'm just showing you how these 5 carboxylases work in our body. They all feed into the Krebs cycle. All of these must be covalently attached to biotin, which occurs via that holocarboxylase synthetase. And then when the enzyme has performed its function, they take the biotin off, which occurs by that biotinidase. So now for the second function, where biotin binds to histones, which alters the gene expression. So this looks similar to my niacin DNA molecule. You imagine this line is the DNA, and there are histones attached onto it. Each histone has some tails on it, and the biotin can attach onto the tails. This helps for gene expression, and it's important to note that we still need covalent bond attachment, and we still need that holocarboxylase synthase to covalently attach those. So if you don't get anything else from this video, biotin has to be covalently attached to the protein partners. Now, what happens if I don't have enough of biotin? You're going to see some symptoms. The one may be lactic acidosis, which goes back to that image of all those carboxylases playing into the Krebs cycle. It's not able to go into the Krebs cycle. We'll have thinning of hair, loss of hair color, a skin rash, neurological problems. And then we can also have deficiencies. So, specific holocarboxylase synthase deficiency. That means that all 5 of those carboxylase enzymes will lose their functions. And with that big image, we see that this is needed for life. These 5 carboxylases are needed for life. So with holocarboxylase synthetase deficiency, we won't have any of these. We also will see a biotinidase deficiency, and that's where we're not able to absorb biotin well. It's like you've never even eaten it before, basically, is how your body sees that. So we do need biotin. It is very important, and that is it for biotin. If you found this video helpful, like and subscribe to join me for all of the other videos that we have coming up.